We're going to do the first question from the following paper, which is 970151, paper 5. It's planning, analysis, and evaluation, and it's May-June 2019. Now, the question reads that a student investigates the charge Z plus carried by aqueous manganese ions. So what you have is you don't. So this is the key point of the entire question, which is that you're trying to investigate what is the charge on Mn. That's not given. It's C plus. That this is what you are investigating. The electrochemical cell shown is set up for this investigation with the following two half cells. The first one is a standard copper 2 ion copper half cell, and the other one is a half cell made from manganese and Mn2 plus. Now I've written down the two electrode reactions as well. The copper ion copper half cell, so it's copper 2 plus in equilibrium with copper in one of the half cells, and the other one was a manganese and Mnz plus. So it's Mnz plus gaining Z electrons. We don't know what Z is to form Mn and vice versa. So they are in equilibrium with each other. So let's have a look at the two half cells, two electrodes. There's copper and copper ion over here, and there is manganese and Mnz plus over here in this half cell. So you have two half cells, and the question part A states label the terms P and Q and state the concentration of the copper 2 ions solution in the copper half cell. So I've labeled this one. This is the voltmeter, and this over here, remember, two half electrodes are connected. Salt bridge is very essential for completing the circuit. The other thing that we were being asked is what is the concentration of copper 2 ion solution in the copper half cell. Now, to find that out, we need to sort of go back and we need to read this. Remember that the copper electrode was a standard copper electrode. The word standard is used. It's a standard copper electrode, copper ion, copper half cell, and E naught. So that's being done under standard conditions. Now, remember, under standard conditions, the solution is going to be 1 mole per decimeter cube. So the concentration of the copper ions in the solution, because it's a standard electrode, this one, not the other one. The other one is not mentioned as a standard electrode. This one is. So standard electrodes have standard conditions. And you can even see that this electrode is not under standard conditions because the concentration is given as 0.5 mole per decimeter cube. Hence, it's not under standard conditions. Let's move to the next part of the question, which is that during the investigation, the student plans to use solutions of Mnz plus of lower concentration than 0.5 mole per decimeter cube. And now you're being asked, calculate the volume of 0.5 mole per dm cube Mnz plus needed to prepare 100 cm cube of 0.2 mole per dm cube Mnz plus. Now let's figure this out. So we have this original solution, which is 0.5 mole per dm cube Mnz plus, and we need to create this solution from it. Both solutions, one solution is being made from the other solution. So this is Mnz plus, this is also Mnz plus, and we need to create this particular solution from this solution. So this is dilution that's happening. You can see that the concentration of Mnz plus over here is greater, and the concentration of Mnz plus over here is lesser. The first thing I'm going to do is, I have this solution, I can figure out the moles in this solution. The moles can be found out using concentration multiplied by volume. We can do that, and it's going to be concentration is 0.2 and the volume is 100 cm cube. I'm going to divide that by 1000 so that it's in dm cube, and that is going to give me moles present in this solution. So I'm getting 0.02 moles. There's 0.02 moles of Mnz plus that are present over here, and all those moles are coming from this. Remember, I'm diluting it, which means that somewhere over here I'm adding distilled water. Distilled water is being added, so I am diluting this solution into this solution. Now, these are 0.02 moles. all these moles would be coming from this solution. So I'm going to use the exact same formula because I know the concentration of this particular solution. The concentration is given. So I'm going to use the same formula, which is moles n is equal to concentration into volume. And if we use that, we already have the moles. We needed zero point zero 0.02 moles. The concentration of this solution is 0.5 mole per decimeter cube. And you multiply that by volume. And if you solve for this, the volume comes out to be, so on my calculator, I'm getting 40 cm cube. I've converted this into dm cube as well by multiplying by 1000. So the answer is 40 cm cube. So remember, when you're diluting solutions, one solution being made from the other solution, just make sure that the trick is that the moles that are present in this solution are all coming from this solution. So the moles are going to be the same. The rest is water. So you have a 100 cm cube solution. So you're taking 40 cm cube of this solution and then you're adding distilled water to dilute it. So you're getting 40 cm cube. That's the amount of Mn plus that you would need from the original solution. Let's move to the next part. The next part is describe how using a 100 centimeter cube volumetric flask the student should prepare exactly 100 cm cube or zero point 0.2 mole per dm cube Mnz plus using the volume of 0.5 mole per dm cube Mnz plus calculated in B1, which we just did using standard school or college apparatus. So basically, the whole process of dilution, we need to explain that. Now, here's your apparatus, here's your basic apparatus. There's going to be a burette, and you're going to pour 40 cm cube. You're going to add the zero point 0.5 mole per decimeter cube Mnz plus, which is your original solution, in the burette, and you're going to try and measure or add 40 cm cube. Exactly. Burette is very accurate. So that's the first thing that you're going to try and do. So you're going to pour 40 cm cube of Mnz plus 0.5 mole per dm cube, the original solution, into a volumetric flask. Remember, a volumetric flask has only one marking. Uh, so take a 100 cm cube volumetric flask because you're basically asked to prepare a 100 cm cube solution. So you're going to do just that. You're going to pour the solution. So let's say the original solution has been poured and this is your volumetric flask after pouring 40 cm cube. What's the next step? Get rid of the burette. You've added 40 cm cube. Now you're going to dilute it. Now you're going to add water to it. So the next part is fill the volumetric flask with distilled water up to 100 cm cube mark. And always remember to use distilled water, and always remember that solutions are always made in volumetric flask. So that is going to get you your 2 marks for this question. And remember, dilution is always done in this way. Make sure you get an idea of the process of dilution, of taking a much more concentrated solution, and then this is the concentrated solution, and then diluting it to get a solution with lesser concentration. The reason most of the time this is done is that bigger quantities are easier to measure. If you want to make a more concentrated solution, it's going to be more accurate because you're measuring bigger masses. Smaller solutions, like 100 cm cube or zero point 0.2 mole per dm cube, the concentration is so less and the mass of Mnz plus would be so less that it would be very difficult to make the solution directly in the lab. So you always make solutions with much higher concentration that contain much larger quantities of Mnz plus because they're easier to manage, easier to measure, and they're more accurate to measure. And then you start diluting by adding distilled water. You start diluting and start getting these more dilute solutions that contain a lot lower concentration of Mnz plus. Let's now move to the next part of the question, which states that the cell potential of an electrochemical cell is measured. The zero point 0.5 mole per dm cube Mnz plus is then replaced by the zero point 0.2 mole per dm cube solution, and the cell potential is measured again. This is repeated for other lower concentration of Mnz plus. All measurements are made at 25 degrees centigrade. So he's using standard conditions to make these measurements. And also remember that every time he's measuring the E naught cell, the concentration of Mnz plus is continuously decreasing. Now remember the equilibrium, that is, this is your electrode over here. The potential over, the concentration of this Mnz plus solution is continuously decreasing. So you have this equilibrium going on over here. There's a manganese electrode, so that's Mn. and that's in equilibrium with Mn plus ions. So it's Mn plus gaining Z number of electrons to form Mn and vice versa. So the reaction is at equilibrium, and you are constantly decreasing or lowering the concentration. So, so the concentration of Mn plus is being lowered. Now, Le Chatelier principle suggests that if you try to decrease the concentration of Mn plus, the equilibrium is going to shift to the left-hand side. And if it shifts to the left-hand side, it's going to produce more electrons. More electrons are going to be produced. And this right-hand electrode, this Mn plus Mn electrode, its potential would become lower because more electrons are going to be produced. It's going to become more negative. So potential so electrode potential is going to be it's going to become lesser and lesser. It's going to decrease. And this side is constant, I think. It's copper 2 ion electrode. The data booklet suggests it's 0.34 volts. So this potential over here on the left-hand electrode, it's pretty much going to remain the same. You're not doing anything to this. The only changes that are happening to this Mn plus concentration over here. Now, the next thing he's doing is that the results of the experiment by lowering concentration are shown in the table. Complete column 3 of the table, calculate log Mn Z plus to 2 decimal places. Complete column 4 of the table, calculating E electrode potential of each manganese half cell to 3 decimal places. So be very careful. Read the instructions carefully. This is 2 decimal places, and this one over here is 3 decimal places. So always remember to follow the instruction in paper 5 very, very carefully. Now, when you're trying to fill the table, you can do your calculations. Everything is provided. This over here, let me explain this equation. Although you don't really need to understand this, you've been given a formula to calculate the electrode potential of the manganese half cell, which you have to do over here. So you can use this equation. The E cell is given in this column over here. Put that in, and you're going to get the value of the potential of the manganese half cell by just using the formula. There's no need to understand this formula, but I'm going to explain this formula anyways. The other one is you need to calculate the log of the concentration of Mn plus. Mn plus is provided over here, so you just have to press the button in your calculator and you're going to get the value over here. This should be to 2 decimal places and this should be to 3 decimal places. So now allow me to explain this formula, which for this question you really don't need to. But I'm going to explain this formula. Remember, he's calculating the E cell. So if we go back and have a look at the E cell, the E cell potential is the potential difference that you have over here. So if I write the E cell, it's higher potential minus lower potential. So one of them is 0.34 volts. The other one is we're not sure what the other one is. So I'm going to take it as X volts. So if you try to calculate the potential difference, it's going to be higher potential minus lower potential. So it's going to be X and minus 0.34 volts. So that's the potential difference, X volts minus 0.34 volts. So if you make X the subject of the equation, then your expression would be the same as the one that's given over there. It's going to be X volts is equal to E cell plus 0.34. So that is going to be your potential for the manganese half cell if you calculate the potential difference and put it equal to E cell. So again, I'm going to insist there was no need for this background. You don't need to do that. The table is in front of you. In most P5 questions, in almost all P5 questions, you just need to follow the instructions. A lot of times, I mean, this over here is part of your syllabus. A lot of times you're going to get questions where this entire thing, whatever the concept is, it's not in your syllabus and you haven't studied it. So remember to follow the instructions carefully. There's nothing to this. The table is provided, Mn plus concentration is provided. You're being asked to calculate the log of that, and the E cell is provided, and you're given a formula, and you're being told to use these values and calculate the electrode potential over here. So you just have to use these formulas and put the values in, and you're going to fill this table. So I'm going to try and fill this table now. Now here you can see that I've calculated all these values. I've done all the working. These values, the ones that are given over here, they've been calculated. Simply taking the log of this, Mn plus, I put in the values, took the log of it, and I made sure that I rounded it off to 2 decimal places because they had explicitly told us that these values must be 2 decimal places, and they had explicitly told us that the values of the electrode potential that we're going to calculate, they should be up to 3 decimal places. So make sure you do that on your calculator. These values were obtained by using this equation. I put in the E cell, which is given over here, and added 0.34 volts to it, and I got the manganese half cell. So these values were calculated. All of these values were calculated in this way, and I filled up the table. And once I have gotten all these values, so the experiment was basically lowering the concentration of Mn plus, as I discussed earlier, and we are measuring the potential of the manganese half cell, and we're also taking the log of the concentration. The next part, and remember, it has nothing to do with your understanding of electrochemistry. You just had to follow the instructions. Remember, follow the instructions that are given in P5, and you would be fine. The next part is you're being asked to plot a graph of each electrode potential of manganese half cell y-axis and log of Mn plus x-axis. Use a cross to plot each data point. Draw a line of best fit. So now you have a graph, and you have to plot in all these values. The axis, everything is labeled. Now, usually the new graphs that you get in your latest P5s, you don't even have to choose the scale. The scale is already chosen. Remember, if you had to choose a scale, make sure that the graph covers more than half. It's more than half covered, or maximum area of the graph. You don't need to draw very small graphs, and it should be contained. So 70% of the graph must be covered. But over here, the thing is easy because the axis, the labeling, everything has been done for you. What you just need to do is you need to plot these data points, x-axis and y-axis. I think the x-axis was log of Mn plus. So that has all these values over here. For example, let's pick the first one. It's minus 0.3 and minus 1.189. So minus 0.3. Minus 0.3 would be, so now be very careful when you're reading this scale. Make sure you know how many boxes, what does one box represent. Over here there are 20 boxes, so it represents a value of 1. So 0.3 would be 6 boxes. So it's going to be 2, another 2, another 2. So 0.3 would be somewhere over here. So that's 0.1, then 0.2. 0.1 would be represented by 2 boxes, so 0.1. Then it's, let me mark that, 0.1. Then you have 0.2, and the next one is 0.3. So that's 0.3. Now on the y-axis, your value was minus 1.189. So let's have a look. You have minus 1.18, and you were saying 9. Now these are 10 boxes. So 9 means, what does 9 mean? So one box over here would represent 0.001, because this is going to be 1.181. This would be 1.182. Now we were looking for 1.189. So that would be somewhere over here. So our cross, our value would be at the intersection of these 2 points. And we're going to mark it with a cross. So put a cross over there. As they follow the instructions again, because they had explicitly told us to put a cross over there. Remember, in reality, you're not going to draw these lines. What you're going to do is you're going to put a scale over here. It's better to actually kind of draw very, very light lines so that you're accurate. That's a good practice. Put your scale over here, because it's very hard to figure out which box it is. So put a scale over here, draw a very, very light line over here, and put a scale on the other side, draw a very, very light line over here, and where they're intersecting, that's your cross. That's where your cross is going to be. So I've now plotted the second point as well, minus 0.7 and minus 1.201. Again, minus 0.7 is over here, and 1.201 is over here. Drew lines, and that's the intersection. So that put a cross over there. And let's fill this table up. Now here I've plotted all the graphs. Remember, use the same technique that I've used over here. Remember, draw very light lines with your pencil on the x-axis. Plot the x-axis values, the ones that are given in the table over here, these values over here. Plot these first and draw these lines. Draw these straight lines that extend all the way to the bottom. And on the y-axis, plot those points and draw these lines. It's very easy to get these points incorrect, mark these points incorrectly. So make sure you use this method, draw these light lines with your pencil, and where the lines intersect, those are your points. That is where you're going to put cross marks. And this is the way you're going to be more accurate with your markings. So I've plotted these values, and the next step is the question is asking us to do what? It's asking us to draw a line of best fit, and that is what I'm going to do now. Now, here you can see that I've drawn a line of best fit. Remember, when you're drawing this line of best fit across through all the points, just remember it's not important that all the points are on the line or maximum number of points are on the line, but the points should be equally scattered on both sides of the line. So the points should be equally scattered, and that is how you draw a best fit line. And they are going to be anomalous points as well, because if you look over here, there's this point over here that is very far from the line. So you can't really cater to all the points. If a point is coming out too far off from the line that you're trying to think of, then ignore that point. That's an anomalous point. Something went wrong in this experiment. And the question, if we read the question further, they're going to ask about this point much later on. I'm going to circle this. Now let's move to the next part of the question, which is D part one. Circle the most anomalous point on your graph, which we're going to do, which I just explained right now. The most anomalous point is this one. It's really far off from the line, so I've circled it. That's one mark. Now, the student is careful to ensure that all the solutions used are at the same temperature in all experiments. Suggest a possible explanation for the position of the anomalous point circled in D1 relative to the line of best fit. So we need to explain why you're getting an incorrect value over here. Uh, so what? Uh, so either this value is coming out to be incorrect, or the y-axis is incorrect, or the x-axis is incorrect. So either of the two values, for example, this should have been much lower over here on the y-axis. So the potential measured was probably not measured accurately. Or the other thing is that the MnZ plus concentration that is calculated, it might not have been calculated correctly. And this point was actually over here. The concentration was not measured accurately, which is why you're getting an incorrect value. So I will just quickly give you an explanation for why this point is. We need a reason for why this point is over here. This point should have been more forward. So that means that the x-axis value is coming out to be lower. It should have been, this point should have been slightly more to the left. So what we can do is that the concentration, what is plotted on the x-axis, it's the concentration, which means that the solution might be dilute. Would be too dilute, which is why you're getting a value. The point is coming out to be more to the right. So it should have been more to the left. And also remember one thing, that when you're talking about, now this is an important point, when you're talking about the anomalous point, remember that the E cell over here that you calculated, that's the dependent variable. So since this is the dependent variable, there can be no error in this. I mean, uh, the outcome might be wrong, but the error that you have in your values, that's not coming from this. This is the dependent variable. You probably made an error in your independent variable over here on the x-axis. So when you're searching for why your points are not coming out to be correct, because these are the variables that are in your control. The MnZ plus, that's the concentration of MnZ plus is in your control. So you probably made a mistake over here. The y-axis is obviously going to come out to be incorrect because you made an error over here, because the E cell over here on the y-axis was dependent on your x-axis. So remember, always search for errors in your independent variables, the ones that you are controlling. You probably ended up making a mistake over there, which is why the outcome is coming out to be incorrect. So let's focus on the point. So never actually look for errors in the dependent variable. Always look for errors, the mistakes that you probably made in your independent variable. Now this point over here, the correct plotting of this point should have been, it should have been on the line, which means that in reality this point is probably over here on the line, but you incorrectly plotted it below the line. So in reality, the concentration is probably lower. Remember, this is log. So if you go more towards minus scale, that means the concentration is actually lower. So in reality, the point is actually much further away, and you have actually plotted it incorrectly. So you are using a more dilute solution, and you think the solution is not dilute. So the point should have actually been, in reality, the point is actually much further away, much forward in this direction, and you're using a more dilute solution, which is why you're getting an incorrect value. So I've written the answer, the point is below the line, so a more dilute solution is being used in this particular experiment. You think it's not dilute, but the solution is in fact actually more dilute than what you think it is. Let's move to the next part of the question, which reads that your graph is a plot of E against log of Mnz plus concentration and can be analyzed using the Nernst equation at 25 degrees centigrade. So you're provided with the Nernst equation and you're given the entire formula where everything is described. Z is the value of the charge carried by the manganese ion, so that's the number of electrons. E is the electrode potential, the non-standard electrode potential. E naught is the standard electrode potential. Now use the Nernst equation and your graph to find the standard electrode potential E naught of the manganese half cell. Now remember, always convert the equation. If you're given an equation, a relationship, convert that equation because it's always easier to plot straight lines and derive data from straight lines. So every equation can be represented in the form, even if it's a non-linear equation, it could be made to represent in the form of y is equal to mx plus c. So if you do that, it's going to be this is going to be your y. This is m, the gradient. Log of m and z plus, if you look at your graph, that's your x. So this is mx. And this is your c. So y is equal to, so this equation over here, y, E was the, let's go back to our graph and let me show you the axis. Electrode potential E was plotted on the y-axis, and log of m and z plus was on your x-axis. So you have your, if you go back to our Nernst equation, you would notice that E is your y-axis, x over here is your log of m and z plus. This m over here must be the gradient. This thing over here must be the gradient m, and c is the y-intercept. So E naught is the y-intercept of the graph. So any nonlinear graph can be made to, it can be, if you plot it correctly, you can make it look like y is equal to mx plus c, and it could act as a straight line. So E naught over here is your, it's coming out to be your y-intercept. So I'm going to go back and I'm going to check where the y-intercept is. Now the line, I did not draw the line completely, so let me completely draw the line first. So here you can see I've extended the line, and the value is coming out to be equal to 1.18, and this is 1.19. So the two boxes, so it's 1 minus 1.182 volts. So let's go back. That's my E naught over here. So I'm going to write the value, which is coming out to be minus 1.182 volts. That's coming out to be my y-intercept. Let's move to the next part of the question, which is determine the gradient of the graph. State the coordinate of both points you use for your calculation and record the value of the gradient to three significant figures. Make sure get the significant figures right. So let's draw the gradient of the graph. So here you can see when you're trying to draw the gradient, let's make 2 points, one over here and the other one at the top over here. Make sure you draw these construction lines. Make sure you draw a triangle where you have your y, change in y, and change in x. Make sure you clearly show these construction lines. This triangle has to be shown. The 2 points that you're using, because you're going to calculate change in y divided by change in x. So make sure you mark those points very, very carefully. Now this point over here, if you look at this point, the y-axis is coming out to be minus 1.21. I'm going to write that down over here. And my x-axis is coming out to be, if I have a look at my x-axis, then the x-axis value, let's follow this line, it's exactly minus 1. So these are my 2 points over here. And the other point that I'm taking is this one over here. The value that I'm getting for this point that I've marked over here is this point over here is minus 1.25 and 4. So this is minus 1.25 on the y-axis. And on the x-axis, the point is, let's follow this line. So the point is, if you look carefully, this point over here, remember to draw these lines. It's much better if you sketch a very lightly shaded pencil line. That would make things much easier. So it's around minus, it's I think minus 2.5 in the middle, and 2.52. Let's take that as minus 2.52. So this one is minus 2.52. So I've gotten my 2 points, and I'm going to use these points to calculate my gradient now. Now, here you can see I've the 2 points over here, and I'm calculating the gradient, which is y2 minus y1 divided by x2 minus x1. And if I solve this, the difference in y-axis, the difference in x-axis, the gradient comes out to be 0.0289. Up to three significant figures. So they had told us to follow the three significant figure. I've quoted the value. That's the gradient over here. The next part of the question is that we need to use your answer to F1 and the Nernst equation to calculate the value of Z to three significant figures and give the formula of the magnesium ion. Your calculation must show the use of the Nernst equation. If you're unable to calculate the answer to Fi, you may use the initial value 0.0197. This is not the correct value. So now we need to calculate Z. What is the value of C? So let's go back and have a look at the Nernst equation. Remember, we have our gradient now for the equation. So we have M. So what was M? M was 0.059 divided by Z. Z is the value of the charge carried by the manganese ion. So we need to figure out Z. So remember, y is equal to mx plus c. We wrote the equation in that form. And we found out that this 0.059 over z was your m. We have the m. We have the gradient. So I'm going to use this 0.059 divided by z, and I'm going to make it equal to the gradient that we just calculated over here, which is 0.0289. So let's have a look. 0.059 divided by z. So let's do our calculations. 0.059 divided by z, and that is basically our m in the equation. And the m that we calculated was 0.0289, which we just did. So 0.028 and 9. So my z is going to come out to be, let's find out what z is going to come out to be. Z would be 0.059 divided by 0.0289. And my value comes out to be 2.04. That is what I'm getting. Now, obviously, it's an experiment and my values can be off a few decimal places. Now, the charge on the ion has to be a whole number. You already know that. Any charge on the ion has to be a whole number. So, this 2 indicates that the charge on the manganese ion must be plus 2. Because in the Nernst equation, it was already clearly mentioned over here that the Z is the value of the charge carried by the manganese ion. So we have figured that part out. We figured the value of Z, and we figured out that if it's coming out to be 2.04, then the charge probably must be plus 2. The next part of the question states that lower M and Z plus causes the value of the electrode potential of the manganese half cell to become more negative. Suggest why this happens. So lower M and Z plus concentration is affecting it's affecting the electrode value, and it's becoming more negative. Now, if you go back and have a look at the cell, earlier we discussed that this was the reaction on the on the right hand electrode that was happening. We can go back and have a quick look at the first part. This was what was happening. There was manganese, the metal, in equilibrium with Mn plus. Now we know what Z is. So it was Mn plus gaining electrons to form Mn and vice versa. They were in equilibrium, and whatever the potential that was over here, that was the potential that was developed because of this reaction or equilibrium that was taking place on the right hand electrode. So let's go back and read the question again. It says that Mn lowering Mnz plus. So if you lower the concentration, now we are lowering the concentration. The equilibrium, remember, it's an equilibrium reaction, so the equilibrium would automatically favor the lower concentration side, more Mnz. If you try to decrease Mnz plus, Mn2 plus now, the equilibrium would try to make more Mn2 plus. So the equilibrium would shift in the backward direction, and if it shifts in the backward direction, more electrons are produced, which means that the potential would become more negative. So there are going to be more electrons, which would cause the potential on the electrode to be more negative. So equilibrium shifts to the left and more electrons are produced. So that is the answer to this question. And that pretty much completes the 16 mark first question of this paper, summer 19 question paper 5-1.